Every day you do this. You ask a question and the answer just appears. It feels instant. But behind that one response is a chip the size of your palm that can cost over $30,000. And large companies use tens of thousands of these chips at once. That's billions of dollars in hardware. And it's how, in just 5 years, Nvidia became a $5 trillion company worth more than the entire GDP of countries like France, Germany, or the UK. But here is what most people don't realize. AI is not just a software problem. It never was. The real race is actually happening inside the silicon. And it comes down to one physical limit that no algorithm can fully solve. Every time you ask AI a question, it has to do some work. And that work is not complicated math, but billions of tiny calculations. Multiplying numbers, adding them together over and over again. So what is actually happening under the hood is this. When you ask a question, your words are converted into numbers. And then those numbers are pushed through massive grids, where values are multiplied and combined, layer after layer, until an answer emerges. And modern AI models don't just do this once. They do it across hundreds of layers, sometimes more. Every layer repeating the same kind of computation for every single word they generate. So even a simple question turns into billions of operations. Now generally, when computers need to do math, they use the CPU, the brain of your laptop or phone. CPUs are incredible. They can run your browser, play your music, manage files, and handle complex logic, all at once. But a typical CPU only has around 8 to 32 cores. And that's fine for most tasks, but AI is not that type of task. Running an AI model is like trying to prepare a massive meal with just one chef. You can have the most skilled chef in the world, fast, precise, incredibly efficient, but if you ask them to cook for 10,000 people alone, it just doesn't scale. What AI needs is not one very smart worker, it needs thousands of simple workers, all doing small pieces of the job at the same time. And this is where parallelism comes in. Take something simple, like multiplying two small grids of numbers. You can do one operation at a time. You go step by step, one cell, then the next, and so on. But if you have multiple workers, you can split the problem. Each one handles a small piece, all at once. Instead of doing 9 steps in sequence, you do all 9 in parallel. And GPUs are built exactly for this. Instead of a handful of powerful cores, they have thousands of simpler ones. On a modern AI chip, you are not working with 8 or 16 cores anymore. You are working with around 15 to 20,000 cores, each one taking a tiny part of the computation, all running simultaneously. That's why a calculation that might take seconds or even minutes on a CPU can finish in milliseconds on a GPU. Not because it is a different math, but because it is happening everywhere at once. And that's why these models run so faster in GPUs. Now it seems like we have solved the problem. Just add more cores, do more work in parallel. But there is another problem. You can just throw 17,000 workers into one room and expect everything to run smoothly. That will be chaos. So the GPU does something much more structured. It organizes. Instead of one massive pool of cores, the chip is divided into smaller groups. Think of them as mini kitchens. Each one has its own team of workers, its own small workspace, and its own local storage to keep things moving quickly. Inside a modern AI chip, there are over hundreds of these mini kitchens, what we call streaming multiprocessors. And all of them run in parallel. Now remember that massive computation we talked about. The GPU does not try to solve it all at once. It breaks it down. Imagine taking a huge problem and slicing it into smaller pieces. Each mini kitchen gets one piece to work on. They load a small chunk of data, process it, and pass the result forward, over and over again, like an assembly line. That is how thousands of cores stay coordinated. Each group handles its own part of the problem, using its own local data, without constantly interfering with others. And when all those pieces come together, we get the final result. But that only works if each team has the data it needs. And that's where the another problem begins. Let's go back to our restaurant example. You have hired around 17,000 chefs. Every single one of them is ready, knives sharpened, aprons on. They could cook an incredible meal. But your ingredient delivery service is painfully slow. 1 carrot at a time through a single door. What happened? Most of your chefs do nothing. They just stand there waiting. And suddenly, the bottleneck is not cooking anymore. It's delivery. This is exactly what happens inside an AI chip. Modern AI GPUs can perform tens of trillions of calculations every second. But the data those calculations depend on has to come from memory. And memory such as the RAM in your computer is not built to keep up for that. So even though your cores are incredibly fast, they spend a lot of time idle, waiting for the data to arrive. This is called the memory wall, and it's one of the biggest challenges in modern computing. For years, this gap kept growing. Computations kept getting faster, but memory could not keep up. To solve this, engineers brought the memory very close to the chips, which are called high bandwidth memory or HBM. HBM stacks memory vertically, like a tiny skyscraper, and that stack sits right next to the GPU on a shared base called an interposer. Now through those interposer, there are thousands of connections that can move data at the same time. The result is a massive jump in bandwidth. Normal memory delivers around 50 to 70 gigabytes per second, where HBM delivers over a terabytes per second. That's more than 20 times increase. And it works because those stacked layers are connected by thousands of tiny vertical pathways, all transferring data at the same time. And that's why these chips are so expensive. A big part of the cost comes from this advanced memory system, because without it, those 17,000 cores would be sitting idle. So when you look at ChatGPT, it's easy to focus on the intelligence. But now you know what is actually underneath it. Thousands of cores organized into teams, fed by memory that delivers data faster than almost anything else humans have ever built. All of it working together just to produce your answer. Because in the end, this is not just software. It never was. The algorithm gets the credit, but the chip does the work. And we're still figuring out how far that can go.